computer. Perfect. Okay, let me see. Let me open the to be here. Let me open the presentation. Preview. Oops, we have a problem. Where is it? Downloads. No. Documents. Let me try it here. Okay. My apologies, because I thought I had it. I had it. Should be. No, I sent it by email. Let me see. I have more than one lecture today, so FIS 140. No. Oh God. No. Apparently, I did not upload it. Let me see. Let me see if I can join you from the iPad in the class. And how would I do that? I would do Zoom. I need the meeting ID, which is here. Let me see, it's here. No. Do you have the meeting ID at hand? Let me see. I don't know if I can join from here. Let me see. Where's the meeting ID for this? No, I don't see it. Do you have it, Ismail?
The meeting ID?
Yeah.
Sure, let me get it.
Because if not, I have to get out of this thing.
Well, I have the meeting link that you sent us at the beginning of the semester. Would that be okay?
Yeah, but let me see how. Yeah, but okay, there you go. Let me see the number.
You could probably resend it to your mail, so you could receive it from there. And
no, I have it. I have the number here.
oh, all right, perfect.
I think it should work. The meeting ID is 886. Since I want to use the other computer, 137. Okay. Okay. No, where do I have the presentation? Oh, this is ridiculous. Where's the lecture? Lecture 10. There it is. Okay. Let me go to much better now. If I put that, perfect. Okay. What? No, wrong lecture. It said lecture 10. This is not the lecture that I want to be in. My apologies. This has been in, this is lecture 6. No. Where is it? I lost the lecture actually.
Oh, isn't it in Aula?
No, here it is. It was in front of my eyes actually. So no, this is Solidos. Good. No, I don't have it in Aula. This is strange. Why don't I have it? I'll just prepare the lecture. I don't. Oh, I was reading. No. This is a fragment. So this is ridiculous. Let me. My apologies. I don't know where this class is. Oh, maybe I did the PDF. Where would the PDF be? Here. PDF viewer. Okay. I can start with this one because this is part of the lecture today.
I do remember that you had mentioned the last class, this slide about muons.
Yeah. So this, this is the last class. It's not this. I will have to find the rest of it, but let's start here. So the question is this one: why are we bombarded by muons? Okay, and the thing is the following. Muons are, I will read the problem. So muons are unstable subatomic particles that decay to electrons with a mean lifetime of 2.2 microseconds. They are produced when cosmic rays bombard the upper atmosphere about 10 kilometers above the Earth's surface, and they travel very close to the speed of light, actually 0.9999 c. The problem is we want to address is why we see any of them at the Earth's surface. So the first question is, what is the greatest distance a muon could travel during 2.2 microseconds lifetime? According to your answer in part A, it would seem that muons will never make it to the ground. Let's explore that first, okay? Let's go to, oops. Let's go to the second question here. So this is the muon problem. So the greatest distance traveled is where am I? No. Here it is. Okay. So the greatest distance traveled by a muon is, well, in time t. What is the time t? 2.2 microseconds. You know, we know that they are created about 10 kilometers above the Earth's surface. So in t2 times 2.2 microsecond, it could travel, you know, 0.999 or the speed of light. That it makes no difference for the purpose at hand. So the distance that it will travel will be 2.2 times 10 to the minus 6 seconds times the velocity of light, which is 3.10 to the 8 meters per second. When I multiply those two things, give me about 660 meters. Okay, so anything that is actually generated at the top part of the surface, if it travels by 2.2 times 10 to the minus 6 seconds, it will never make it to Earth because it would only travel 660 meters. Okay, so nothing should arrive. Yeah. So you know, if you do that calculation, you know, you understand the puzzle. But there's a caveat here that the actual lifetime of the muon, those 2.2 microseconds, are measured with respect to a system that is the rest frame of the muons. Okay, so T naught is equal to 2.2 times 10 to the minus 6 seconds on a frame that is actually traveling with the muon. Okay, so you attach the frame to the muon and then you measure the time in there. So the observer on Earth measures a dilated time.
So the question has to do with a different point of reference, not a moving point of reference, but a static point of reference.
Yes, it's a different point of reference, but you know, the time in the reference frame of the muon as seen by a guy on Earth, it's actually slower. 2.2 microseconds is actually much larger in the second reference frames here. See, this guy over here, where I am, oops, I'm not pointing anywhere now. Okay. No, I don't know what happened. Where's the pen? I guess I could use my pen. Okay. This oops, I cannot use my pen either. Why it's not? I don't know. Okay. I think this is a PDF file. That's the reason why I cannot draw on it. Okay. Perfect. Can I do that? No. Okay, now I can draw. Perfect. Close this. I cannot draw now. This is strange. Okay. I don't think I have the ability to highlight my pen here, but I'm going to use this. This time over here. This time over here is the time on the reference frame of the muon. If I place it here, the time seen by Stanley, which is in the train station, essentially, it's much longer. You know, you have to multiply this T naught by gamma, which in the case of 0.999 C, gamma turns out to be 22.4. Okay, so essentially the time it has to travel instead of the 2.2 microsecond, as seen by the observer on Earth, will be 4.9 times 10 to the minus 5 seconds. And in that time, you know, the decaying muon can travel exactly 14.7 kilometers, which is enough to reach the surface of the Earth. Okay, so that's the solution to the puzzle in a sense. Yeah. Let's examine how this works in the rest frame of the muon. So in the rest frame of the muon, it means that now I have a reference frame which has the origin 10 kilometers up on the atmosphere, but you know the x-axis is nailed to the to the atmosphere, to the ground. Okay, so essentially this particle here, you know, this reference frame is fixed with respect to the ground, and this reference frame O prime is traveling at the speed of light. Okay, so in the rest reference of the muon, O prime is the proper length that we have here, because you know this distance from the origin to the surface of the Earth is something that is at rest in this reference system, in the reference system of Earth. And now I'm looking at the same thing as seen by the reference frame of the muon. So what would be the length that I'm actually seeing? It's in the case of length is there's a length contraction. So the 10 kilometers, 10,000 meters, has to be divided by 22.4, which gives us 447 meters. So for the muon, traveling at almost the speed of light, even though in the rest frame of the Earth, they are produced 10 kilometers above the Earth, since the velocity is very high for the muon, it gives the impression that the distance is only 447 meters above the surface. Okay. So in the rest, in that reference frame, if it only has to travel 447 meters, it will also reach the Earth, because it will have this, you know, 2.2 microseconds in the reference frame of the muon to travel. Okay, so it will arrive no problem at the Earth. What I've done below here is trying to use the Lorentz transformation in order to tackle the problem as an example. Okay, because the Lorentz transformation, what it does is transform one event that happens in one reference frame to an event that happens in a moving reference frame, and we know the rules for that. So we only have to define well where the system is. So I call event one is the muon is created in the upper atmosphere, and E2, the muon arrives to Earth. So I only need the coordinates. For E1, it happens that X1, T1, they are both 0. They, you know, just at the moment when the muons are created in the upper atmosphere, I start the clock in my reference frame. And, you know, the way we define the Lorentz transformation, the origin X and T are always coincident. So X prime and T prime will be also 0, which is a nice setup. Okay. And then this system, it's start to travel. Let me see if I can get this guy out of the way. No, I can't. Okay, yes, no. Let me see if I put it here, perfect. Okay, now the muon is starting to travel and it arrives to Earth. So the event 2 happens, I know X2, it is the coordinate in the reference frame of Earth is 10 kilometers, which is exactly this number over here. No, why doesn't it work? Okay, yes, that 10 kilometers. What would be the time 2 when that happens? Well, you know, the time is 10 to the 4th kilometer, 10 to the 4 meters divided by the speed of light, because that's the time it takes for the muon to travel from the origin where it was created and arrive to Earth. So I have that. So now I want to find out what are the coordinates in the X prime system. So I just simply use the Lorentz transformation. The Lorentz transformation gives me X prime times gamma X minus U times this is U, okay, and divided times, why does it say 0.999 here? Where are the Lorentz transformation? Here I have the Lorentz transformation for X is X minus U times T, okay? And I did that, and that is the expression, oh, okay, this is U, this value here is U, and this value here is T, okay, T2, okay, is the time. So X2 prime would be that, perfect. So everything is canceled, and what do I obtain for X2 prime? X2 prime is, it happens at the origin, which is good, because I knew that all the time, because the particle, the reference frame is attached to the muon traveling down. So this has to be 0. Okay, so this is correct. But at the same time, I can get T2 prime, which is this expression here, which is gamma times T. T I know, and X I also know. Yeah. So I just replace everything in this expression. Okay, this is X2. Okay, I bring X2 down, and so I write the whole thing and I find the time. The actual time T2 prime is 1.49 times 10 to the minus 6 seconds. Okay, this time is the time it takes for the muon to travel from here to there. Okay, in the frame of the muon. This time is much smaller than 2.2 times 10 to the minus 6. So the muon arrives to Earth with no problem. And in the frame of the muon, the distance is, well, you know, we know that, 447 meters, okay? So the idea is, I don't know if this was confusing enough, probably too much. But the idea is that you can, if you look at if you define very well the events, you have the X prime here and the X here. So if you know the X, you can find the X primes. And in this particular case, what we did, apart from the obvious one, that the X2 prime is equal to 0, and it comes out naturally out of the Lorentz transformation, is the fact that you can get the time in the frame of the muon, okay, to travel to Earth. So this is the time it takes for the muon to get from here to there, despite the fact that it's 10 kilometers, okay? That is one. Now, the next subject that I have here is the Doppler effect. Are you familiar with the Doppler effect I
am.
Yeah, is the fact that when you have something, you know, a wave which is emitted or a train of pulses of an excitation which are emitted from a moving source, if you are standing still, you will see, you will have the feeling that if the source is moving relatively fast, you will see that the frequency is higher if the system is moving toward you, if the source is moving toward you, because you know each time a beep of sound is emitted, you know, then and with a certain frequency, it's different as if the system was standing still. That is part of the problem that we are going to try to face here. And the other one is that, let me get this out. And the other one is that we have the relativity of time, which is also playing a role. Okay, so the idea is the following: light is emitted from a moving object which is traveling u, and it generates a frequency f naught. F naught is the frequency in the rest frame of the object that is moving. Okay, so the question is, what is the frequency f observed by an observer at rest? Essentially Stanley. Yeah, no, we're referring to him. Okay, so the wavefronts are emitted in the same location in S prime. Well, we know that, yeah, because you know we fix the reference frame in the moving object. Hence, comma, f naught equal to 1 over t naught is a proper time. Remember that we define a proper time something like, oh no, I don't have it here. Yeah, this is actually lecture 10. Okay. So why did I save it as lecture 9? I don't know. Okay, so the idea is that since this is a proper time is the difference in time between two events that happens in the same location in space. The same location in space in the reference frame that is at rest with respect to the event. Okay, otherwise it will be moving. Yeah, but in some reference frame, if it happens in the same time, that those events can be considered a proper time in the reference frame in which everything is at rest. Okay, so this is happening here. So 1 over f naught is equal to t naught. Okay, so t naught is a proper time, the time between wavefront as measured in the rest frame. For Stanley would be something like this. This will be sort of the rest frame measure, because here we have t naught, which is the measure in the rest frame, and this is the event as measured by standing still frame. Okay. Nonetheless, we have not included here the fact that the source is moving. So we have to include the fact that the source is moving, because that is going to affect the distance that the light will have to travel before arriving to the observer that is at rest. Okay, so this is the idea is this is the you know, my model train. This is Stanley here, okay, at the station, and you know, when one light wave is emitted, you know, this is the position that the train has when the front was emitted, and at a certain time when the next front is going to start coming out from the train, the train has already traveled a distance u times t, and the wavefront is at a distance c times t from the original position of the train. So essentially, what does happen is that the light will have to travel a distance which is not ct but ct minus ut to actually arrive at Stanley per each period of time that occurs. So since the motion of the train is actually included, so if we call lambda equal ct minus ut, is the distance that light has to travel before reaching Stanley in each period. So there are many periods of the frequency of the wavelength of the light between the train and Stanley, but for each period, the thing is going to move a bit, so that the actual distance that is required to be traveled for each period will be this distance, okay? Ct minus ut. So the frequency that Stanley is going to be measuring, it would be T1, would be 1 over f, and it will be Ct minus ut divided by c. Okay. What is T? T is the conversion of the proper time, this time over here. Okay, so I do both things. I replace T by the proper expression, which is this one over here. I'm sorry, this one. And, you know, multiply by C minus U divided by C. Okay. And that will be 1 over the frequency seen by Stanley. Perfect. Okay. So I do the algebra here, cancel this guy with that guy, and blah, 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 and obtain this expression. This is the frequency as seen by Stanley. This is the frequency in the moving frame. Okay, this is the frequency in the moving frame, F naught. Okay, so the plus sign here means that the source is actually approaching the observer. Okay, so this is the relationship between the frequency as seen by Stanley, and this is the frequency in the rest frame of the source. Okay, and this way of seeing the Doppler effect includes both things. It includes the time dilation for one thing, and includes the fact that the source is moving. Okay, and let's look for an application of this. So this is light from a galaxy, traveling away from us, is received on Earth. The galaxy is traveling with this gamma. So it's a distance galaxy that is, I said, going away. Yes, going away from us. And in the galaxy, there's hydrogen at a high temperature, and hydrogen has a characteristic radiation while at rest that emits light of this frequency, 21.8 nanometers, okay, which is a sign of, this is the way people find hydrogen in other cosmic objects. If you look at the sun, which is essentially standing still with respect to the Earth, there's a lot of hydrogen there, so you will receive a frequency of 21.8, which is vacuum ultraviolet light. This is a transition between the, if you remember some chemistry, well, you did this course last time. So you see this difference between the ground state and the first excited state of hydrogen, between the 1s and the 2s state. Okay, so what would be the wavelength observed on Earth for this hydrogen transition? Since this is a source that in its own rest frame, it produces radiation of 21.8, and we would like to see what happens when we see it on Earth. So since the galaxy is moving away from us, it implies that U is less than 0. So whatever U I'm using, it should be less than 0. Gamma square, it's 25. So I could, try to get an answer out of this. They're telling me that gamma square is 5. So gamma square is 25. So in that way, I can find out how much is, what is the value of U out of this. So it's U square over C square is equal to this. So essentially U over C is about 0.98. Okay, this is the beta of U over C. But we also know that the wavelength of light in whatever reference is equal to c times t, or c divided by f. Okay, so I go to this expression, and I have to use this expression again. So if I want to write it as a function of wavelength, the only things that I have to do is multiply this expression. It's the same one that it's at the bottom here. This is the same expression, with the difference that, what is the difference? Let me see. I figured this out. Well, this is f naught and this is f, and what I have here is 1 over f. So the c minus u is on top. Okay, that's the difference here. And then, but I have to evaluate this with a u of minus 0.98 c. So I replace u by minus 0.98 c and find out what would be the actual frequency observed on Earth. So instead of measuring 21 point whatever, where was this? 21.8 nanometers, what I'm actually measuring is 2,158 nanometers. This is a radiation that is actually strongly redshifted. When you say that a radiation is redshifted, it means that it goes to wavelengths that are much larger than the wavelength in the rest frame. And larger meaning because for the optical spectra, the longest wavelength is at the red end of the spectrum. So when the wavelength of something is increased due to a Doppler effect, people usually say this light is actually redshifted. Okay, and this is exactly what goes on here. The 21.8 is not a visible light, but the 2,158 it is. It's barely visible. It's barely red actually. Okay, it still it went through the whole visible spectra and almost it goes to the infrared. This is almost infrared essentially, and it's strongly redshifted. And this is what people do to actually measure the speed of far distance objects, because they know they have hydrogen in them and they should be making these transitions. And if you see the hydrogen lines that are not in the correct place, but are actually shifted a huge value, you can, by measuring the difference in the wavelength, you can actually determine the receding velocity of objects in space. Okay, astronomers are very keen in doing that. Let me do some sort of summary so far of what we have seen. Why is this so? Okay, here we go. So I don't want to see this. Oops, I didn't want to do that. Okay. Yeah. I have to place it here. I cannot magnify it that much. Okay, so this is the summary so far. We are measuring length as seen by an observer at rest. This is what we call the proper length, and we are measuring the same length as seen by an observer which is moving. This would be L naught. Okay, L naught. This distance here. Where's the pen? this distance here is essentially the distance in the reference frame that is at rest. And L is the same distance as seen by a moving observer. And what have we obtained already in the last class is that that length actually depends on beta. Beta is actually the velocity that the reference frame has with respect to the one that is not moving, okay? So the red line here, it's the Galileo thing, you know, the length doesn't depend on the velocity of the object. You know, this is the trivial thing that we have believed all the time, but essentially in relativity, it does. So if you are actually, you know, if the system in where the length L naught is at rest, is moving at a velocity very close to the speed of light, what will happen is the length will go essentially to zero, to this point over here. So whenever I measure a length in a system that is moving, I will see almost the same as Galileo will predict, meaning the same length, or definitely always smaller, okay? So Einstein will predict the green line. The interval of time. This is the difference in time between two events that occur at rest in the same position in a reference frame. And what happened when I see that the difference between those two events by a system that is in motion? When the system is in motion, the difference in time will be much larger. So this is the green line. The green line is theory of relativity, and this would be what Einstein would predict, and Galileo would say it doesn't really matter what the velocity of the reference system is with respect to another one, the two inertial frame. The time interval should be always the same. And we have learned that if we use the fact that speed travels always at the speed of light, you know, the green line is the correct answer. Yeah. Let's see this part now. We have the now I have the velocity. Why is this not? Okay, I don't understand this. Okay, here I have it. Now I have the velocity of an object subject to a constant force. So if I do that in the case of a classical object, Galileo would say if that thing has a constant force, it will accelerate continuously forever. Okay, that's essentially what happens. So his prediction of what the solution is this should go as you know, accelerating forever, you know, beyond the speed of light. What is really going on? We know that the velocity of light for an ordinary object with mass, the actual limit is the speed of light. So no matter how do I accelerate, if I'm accelerating constantly, meaning applying a constant force to an object, when the velocity of the object arrives essentially to this point over here, which is you know, very close to the speed of light, you will see a departure from there. You know, you're not going to keep accelerating forever, but the acceleration is actually reduced at every point, and it becomes lower. Okay, even though you have a constant force, you cannot increase the velocity of the object beyond c. Okay. An alternative graph for the same situation is the following that I have here. I'm measuring now the momentum of an object as a function of the of the velocity it has. Okay. You know, when I'm getting very close to the speed of light, what really happens is that the momentum keeps increasing. It keeps increasing, but the velocity cannot increase beyond c. So we have this sort of saturation curve at beta equals to 1, where you get the difference between Einstein and Galileo. Galileo would say this thing will keep growing beyond beta equal 1, and the momentum will keep increasing. The momentum keeps increasing, but not the velocity. This is what happens. This is the difference. If we plot now the momentum as a function of the time at which we apply a constant force, both graphs are the same. It means that the expression that a constant force, what it does, no matter what the velocity is always increase the momentum. And that can make us wonder that there's something strange about the definition of momentum. You know, in classical physics, momentum is equal, I'm sorry. Yes, let's write it here. P is equal to m times b. Okay. But I cannot keep increasing the momentum for forever, as it shows here, because it somehow, this expression cannot increase forever. But you know, something happens when you get to beta equal, or you get close to beta equal 1. What does that mean? It means that this definition of momentum is not really real for velocities are very close to the speed of light. So we have to change it a bit. And the good thing is that there's a simple way of doing that, which is the expression that I have here. So momentum is equal to m gamma times b. If b is much smaller than the speed of light, this gamma thing goes to 1, and we recover what we expect to see in the case this here. See, we recover what we expect to see in the case of classical physics, that momentum is equal to mv. Okay. The force, nonetheless, is equal to dp in dt. And this Newton equation is valid in the case of relativity too. The main difference is we have to change what we put in here for the momentum. So we have made only one big change, and the big change that we have made is we have recognized that we have to introduce this this gamma factor here in front of the velocity in the definition of momentum. In what goes on from here now below, we're going to assume that the velocity is collinear with the force. Okay, so this is fx, and this would be vx, and this will be vx. I didn't write it like that, but it's f and b are collinear. That's the expression. So the expression for the force is equal to the derivative of the momentum, but the momentum now has another term with the velocity dependence. So I have to write it like this. So I have to take the derivative of this object here. And how do I do that? Well, take the derivative by parts. First, I take the derivative of the thing at the bottom here. This is what it is. Then I multiply by the derivative of whatever it is inside, which is this factor over here with all these minus signs, the 2's and the 1/2. We actually raise the exponent to 3/2 here. Well, lower it to minus 3/2 essentially, and then multiply that by the derivative of the velocity with respect to time. The second term is simpler because this one is already been derived, and then multiply by m. The m is out here, so the only term that it really counts is dv in dt. Okay. Okay, here I write it completely again, and look at the coincidence in this thing. What I have done is just multiply this term by 1 over minus b squared over c squared, so I can get the exponents in the bottom part here the same. So from this step here to that step here, the only thing is I just multiply here bottom and top by the same number, which is 1 minus b squared over c squared. Can I get rid of that? Yeah, I can. And so it works perfectly well. So the final expression that we have is that the force is equal to the mass times gamma cubed times the density. Okay, so this is a big difference in terms of relativistic dynamics. Essentially, this is what we're seeing here. So everything is the same. The definition, Newton law, second law work perfectly well, with the difference that let me see. Ismael, do you have a watch somewhere? It may be that we are. How long do we have for the class today?
We should have around 13 minutes.
Perfect. Yeah, it would be enough for me to actually finish what I have to say. Okay, so we have this. Thank you. We have this expression for the force, and we're going to use it to calculate the kinetic energy. How do we calculate the kinetic energy? Well, we know by conservation of energy, which is actually that is also valid in terms of relativity. If we make a certain increase, if we make work over a particle by increasing its kinetic energy, the work that we do should be transferred to kinetic energy, just by conservation of moment. We are doing work over a particle because we are displacing the particle by applying a force to it, and we would like to find how would the kinetic energy increase. So this is the expression. The increase in kinetic energy, differential increase in kinetic energy, is the force times the displacement. And well, I take the force from the expression above, write it here, and multiply by dx. Now I take this differential and write it down below this guy here to actually express everything in this second line here as a function of velocity. So now the kinetic energy will be the integral from 0 to the maximum velocity that the object obtains of this expression, m times b times dv divided by 1 minus d squared over c squared to the 3/2. Okay, and this guy is coming from the force. See, this guy, the 3/2 here, is coming from the force. Okay. Well, this is a very direct integral because this is change the variables a bit, and finally you will be able to follow it up. And why is not doing this? It's a bit cut here. Okay, so it's mc squared over 2 times the integral between 0 and the maximum beta of 1 minus beta squared to the minus 3/2 d beta. Okay, and this is essentially the integral of y dy, and everything replaced. This is the expression that I get. And that this has to be evaluated between the final beta and the initial velocity, which is 0, or the initial beta, which is 0. And essentially I get this expression here, just simply out of the integration. So the kinetic energy is equal to mc squared times this gamma factor minus 1. So you can rewrite it as I have it in the bottom, and essentially when you know, you can rethink the whole thing and say, look, the kinetic energy can be thought of the difference between the total energy of the particle minus the rest energy. What is the rest energy? This term here is, we can be reinterpreted as a rest energy. Why is we call it a rest energy? Because it's an energy that a particle has just by being a mass. So mass is equivalent to energy in this expression from the dynamics that I'm saying here. So essentially I can reinterpret the kinetic energy as the difference between the energy associated to motion minus the energy associated to a rest particle. See, this is a difference. The kinetic energy is a difference from something that is dependent on the velocity minus something that doesn't depend on the velocity. So it's natural to assume that this thing over here that doesn't depend on the velocity is what we call the rest energy. It's the difference between the total energy and the kinetic energy. So the kinetic energy is equal to the total energy minus the rest energy. So this is the expression that we have here. And I have introduced now the m naught. I have changed m to m naught. Okay, m naught, when it has a 0, it means that is the rest the rest mass of the system. Because why I'm doing this? Because we're gonna, in the next line, which is this one, I'm gonna generalize the energy, the concept of mass. I will say the mass is equal to gamma times m naught. If I do that, the total energy is equal to the mass times c squared, which is beautiful, okay? That mc squared, I have to reinterpret this because this is the mass, but this is the dynamic mass, okay? So what is the dynamic mass? Is simply the rest mass times gamma, okay? So this is the expression for the total energy. The kinetic energy is equal to the total energy minus the rest energy. Perfect, no problem at all. It kind of works, okay? There's also a very interesting relationship between momentum and the total energy. Let me see if I can get this guy moved this way. Okay, and it's what we have here. This is the total energy of a system. I dropped the total in because everybody calls E equals mc squared. We know that even from jokes about Einstein. So we're not gonna change that notation, okay? But E is equal to the mass, which is m naught times gamma. So this is the mass times c squared. And then this product, P times C, is also an energy. It has energy units because, you know, if you remember well, the kinetic energy of a moving particle in non-relativistic mechanics is the mass times the velocity squared times a half, okay? So if I multiply momentum times velocity, this has units of energy. And this product in particular, if I write it here, is m naught times gamma times B, this is momentum, that is momentum, times C. Okay, so this is the same thing. Now I want to do the following. Take E squared, take the total energy squared, take this expression and squared, and make the difference between both of them. If you go through that, you know, this is a very simple algebraic thing here. You can actually rewrite this you know, 1 minus b squared over c squared is equal to 1 over gamma squared. So this is, if this is gamma squared, this is 1 over gamma squared. So this term cancels that one. And what do we have? E squared minus p squared c squared is equal to
m naught square c square, which is, what is this? This is the rest energy, okay, square. So there's some sort of relationship, like a triangular relationship here. This is the total energy square is equal to PC square, which is this side here, time plus M0C squared. So this guy square is equal to that guy squared plus, I'm sorry, this guy square, the square here built here is equal to the square here is equal to the square there, okay? So I have built this relationship this is a very interesting aspect, because the rest mass of an object really doesn't depend on the relative velocity of it, but both the energy and the momentum depends on the system you are actually observing at a particular mass object. A massive object being looked by a system that moves at a certain velocity has an energy and momentum that really depends on the condition of motion of that object with respect to the reference frame. But if I take the energy, it doesn't matter what the velocity of the system is. If I evaluate this difference, this is an invariant. E squared minus PC squared, doesn't matter what the velocity of the reference frame is, because what is this? This is equal to the rest mass. And the rest mass of the object is equal to the rest mass no matter what the velocity of the system is, okay? So we can use this to solve interesting problems sometime, and we will use them to work with photons at one point. Photons are particles of light that have zero rest mass. So essentially the energy will be equal to PC, because this part, the invariant part, will be equal to 0, okay? Okay, this is part of it. The next part of it is this factor over here, that the kinetic energy should be the same as the kinetic energy that we know from, from physics 110. This is simply I have the mass times the velocity square, where that nice equation that we have been so familiar with went, Well, it's here, this is the same thing, it's equivalent. The only thing that I have to do is I have to make the velocity low enough, meaning v squared over c squared. If this factor here is very small with respect to 1, what will happen? Well, I could expand this and do the usual approximation that 1 plus x to the n is equal 1 plus nx. Okay, this is the Taylor expansion of the power of the binomial there. So the kinetic energy will then be m0c squared times 1 minus this term here minus a half v squared over c squared. This comes from the exponent minus 1. So the 1 cancels the 1, and the c squared here cancels the c squared there, and we recover the very nice classical expression that the kinetic energy is equal to m0b squared over 2. Okay, this is the key part of it, which is the interesting aspect of this. Now, I have a homework problem here for you. So in general relativity, you can actually create mass, because why can you create mass? This sounds very strange, like something from a different world. And the fact that you can create mass is simply because mass is equal to energy, and energy is conserved. So energy is not destroyed. So if I have certain amount of energy and I go through a process, a strong process like a collision, for example, between two particles, and I can make another particles, okay? And this is at the heart of all the particle accelerators in the world. They're actually looking for new physics and new exotic particles, okay? So here I have an example of that. So the creation of particles. We have two protons, each with a rest mass. This is a rest mass of the proton that are initially moving with equal speed in opposite directions. So why are we doing this? What we're doing here is a p. This is the proton. This is an antiproton. So it's a proton and an antiproton colliding with both with the same velocity against each other. And what happens here? It means that the initial momentum of the system, because what do we have here? No, we have two protons. We don't have an antiproton. We have two protons. Okay, so two protons colliding with each other would be something like that. So essentially, there's a lot of energy here. What is the energy in here? Well, there's the rest energy of the particles that we have m0 c squared times 2. And then there's the kinetic energy. So, or well, you can say there's the total energy of the system is the total energy of 1 times 2. Okay, that's or 2 mc squared. That is the total energy. And the momentum of the system, the initial momentum of this system is equal to 0. The final momentum of the system should always be equal to 0 because the momentum is conserved. Okay, so now you have to do the conservation of energy and the conservation of linear momentum to find out this what would be the energy to create a particle that's called an N naught. Okay, if the two protons and the N naught are at rest after the collision. So before the collision, we have this that has zero total momentum and a certain amount of energy, and at the end, we have two standing protons. The two standing protons here. The protons now here are moving. Two starting protons. But again, I have an invited guest to the party, which is another particle that is also at rest. Why is it at rest? Because the total momentum, the total initial momentum from this collision is 0, so I expect the total final momentum to be 0. Okay, so I just want you to work out, you know, the algebra here and find out what would be the energy. Don't, you know, solve the problem essentially. Considering these two elements here, now you have the definition of the total energy for the system. You have the definition for the linear momentum and whatnot. So this would be something that it's relatively easy to do. In general relativity, nothing is easy to do because when you learn about general relativity, you are actually afraid of writing any equation at one point because you don't think it's going to be valid. So the thing is, forget about that. Everything is valid. The only difference that you have in general relativity is you have to respect the time. Time in one reference frame is different from a time in a second reference frame. And the second difference important in general relativity is, and it's the only thing that is different from classical mechanics, is the definition of momentum. So if you, the difference in time between one reference frame and the next and one that is moving it's due to the fact that the velocity of light is independent of the motion of the source. That's it. That doesn't change. Velocity of light is velocity of light, no matter how you see it. Perfect. And then what else? It means that you know the rest of the relations are all correct, meaning the Newton law is valid. The distance traveled by a particle moving with constant velocity is, you know, the velocity times time. That's the distance it travels. So everything is as you expect in classical mechanics, with the care that you cannot use the time in different reference frames interchangeably. Okay. Or you use the Lorentz transformation, or you use contraction of longitude and or dilation of time as a mean to convert one to the other. Lorentz transformation is your safe bet. because the contraction of length and the dilation of time were both presented as facts, so you can actually obtain the Lorentz transformation. That is sort of the way it was done in my lecture. Okay? So this would be the thing for today. This is the okay. So and what else? Yeah. Okay. I'm sharing here. Let me go back. And now I want to get into here. Okay. And what I could do here is stop share. Perfect. Okay. So this will be the lecture for today, and I guess we don't have classes next Tuesday.
We don't? I thought it was Monday was the day off, not Tuesday.
No kidding. Okay.
Yeah, actually, no, we should have classes next Tuesday if I'm not wrong. I've actually got a test on that day.
You had a test on Tuesday?
I do have. I have a test on Tuesday actually.
Okay. Well, in the location that I am in, Tuesday is holiday, so it's going to be a holiday for me. Okay.
All right, that makes sense. Yeah.
Yeah. And so we're not going to have a lecture. I actually had it like that since the beginning of the year. I thought that Tuesday was Monday was given free simply because of it was a sandwich day between two holidays, and it seems to be that that's not the case. But nonetheless, it's a holiday here, and I'm not
that's completely understandable.
Okay, so we don't, the program doesn't include classes on this Tuesday, and I have something else already scheduled. So we are going to be meeting next Thursday then. Okay.
All right.
Okay, so whatever happens is next Thursday. And I don't know, we are gonna have a few classes before the exam, actually. I don't recall when is the exam or not. So at one point, I hope your friend is gonna make it for the next class, because I wanna make some sort of, an online homework. I'm gonna give you a short problem and you solve it and give it to me. I want everybody to practice the way the exam is gonna be done, okay? Because I'm going to.
All right.
So that's going to be part of the process, and probably I'm going to do it next Thursday. Okay. So try to get him to be here. It doesn't really matter, if he had enough time to look at everything, because he skipped both relativity classes, and he may have a few questions there. But I'm going to make a simple question that basic stuff, some sort of a quiz essentially. Okay.
All right.
Okay, Ismael, enjoy the break, and make good use of the free Tuesday in case of me. You have an exam, I'm sorry about that, but yeah, make good use of the free time. So I see you next Tuesday then, okay?
Next Tuesday. Take care.
Next Thursday, I'm sorry.
Oh yeah, Thursday.
Next Thursday.
We just talked about it. Yeah.
That's what I meant.
Take care.
Okay. Ciao, ciao.